Good evening, Namaskara, Namaskara, Vedantu Karnataka students. Welcome, Yallaru. This is your Captain Shreyas, your physics master teacher, and we are in the KCET series for 2025-2026, and we are in the chapter of ray optics where we are going to discuss about refraction, the bending of light, and the lenses and the curved surface refraction as well. Lot of amazing simulations out here today which you are going to have, and also about lenses. Everything in this class practically you will be understanding, you will be seeing it, you will visualize it, because they say when you see then you understand, you get a feel of the situation. That's what today's lecture is all about. And this is your captain Shreyas, who has been guiding kids for more than 13 years. On to you. Hi Kushmohit, welcome aboard. All the students join in quickly, bega like ಮಾಡಿ, because lecture start aite. Yes, this is for all of you only, and let's begin. Okay, so in case some of you are watching it recorded, no problem, you can leave a comment below so that yes, I get to know your name. All right, or else because you missed the live class, then I will never know you then. Cool. Chalo, let's begin. Hi Gokul, I hope you guys had your dinner. Uta aitu? Okay, uta aitu sir. Fine. Let's talk about refraction first, and then let's define few terms, and then let's see the formulas. I will show you the simulation, everything. Okay, let's begin, my dear students. So, to start off with, refraction is a phenomena of bending of the light as it changes the medium, and in this particular process, the speed of light and its wavelength changes, but the frequency, that is the color, remains same. The color remains the same. The amount of bending depends on a constant of the pair of mediums. That is basically called as the refractive index. That is called as the refractive index. So this is one main theory point which you should know. Now I will obviously explain this to you. Let's understand. Refraction is the process by which the light bends. When it changes the medium, and the speed will change and the wavelength will change, but the color, which is decided by the frequency, does not change. Also, how much it bends depends on what medium are we talking about, and that constant which defines that, how much it bends is called as the refractive index. So let me demonstrate this to you by showing this simple phenomena out here. Okay, as you can see, there is a torch over here which I can move around here, and the top part is air, the bottom part is water, but let's say I make it air. This is also air, this is also air. The ray of light will just go straight, isn't it, my dear students? Yes, Salman K. If you have failed in the midterm exam, don't worry. Let's rise again, Salman. Nothing to worry. We will make you zero to hero in no time. Next 3 months, you give it to me. Strict ane lecture nodi. Every day. Timetable beku. Timetable follow ಮಾಡಬೇಕು. Okay, strictly lectures lectures, okay, follow Madi, assignment solve Madi, all right. Make sure that you are, regular in the classes and be confident. We will make sure that everything goes well. Okay. Krishna, my health is little better. Tomorrow is the last dosage of antibiotics. Yeah. So today also I'm on antibiotics. Tomorrow is the last dosage. Thank you for asking, Krishna. Means a lot. You guys remember. So right now the ray is going straight without any deviation. Okay. Now I change the material. Let's say I make it water. See what happens. This light has bent. This is called refraction. And air or vacuum is considered as rare medium. Water, glass, diamond, etc. are considered dense medium. And when light goes from rare medium to the dense medium, it bends. If you see the normal, bends towards the normal. But just imagine if I had made this water and this is also water, then now change. So the light will travel straight. There has to be a change of the medium. Let's say I make this water into air. Oops. Okay. Can you see the light has bent away from the normal because it has gone from a dense medium, which is water, to a rare medium. So it is very clear that when light goes from a denser medium to rarer medium, it bends away from the normal. Normal is the perpendicular drawn. But when light goes from a rare to a dense medium, it bends towards the normal. This was 34 degrees, it became 25 degrees. I hope you can see that. Correct? Very good. Also, second point, what did I say? The color will not change. Can you see red remains red? If it was yellow color or green color, green remains green. If it was violet or blue, it remains blue. So color does not change. What will change then? Speed. Here, this is rare. This is dense. So difficult for light to travel. So here it will travel fast. Here it will be slightly slower. But if I make it the other way around, let's say this is water and this is air. Then what will happen? Here it will be slow, and as it goes into the rarer medium, it will become fast. It's like open road versus congested road. Dense medium means congested road. So this is congested, this is little bit free, express highway types. Okay, so that's what happens. So let's bring it back to air and water over here. That was the second point which I mentioned. Third point which I mentioned was, it depends on the pair of media, and that is a constant called refractive index. Right now I have chosen water. If I choose air, it doesn't bend. Instead of water, if I choose something else, notice this angle is 25 degrees right now for water. Let's choose glass. Do you see it changed 22 degrees because this medium changed. What if I choose some another mystery medium? Oh, it has changed even further, 13.5 degrees. Similarly, some other element, some other material, 23.9 degrees. So if I choose different material, it changes accordingly. I can choose the above one. Let's say some weird material, mystery B or mystery A, let's say. You can see the light has gone from here to here. From this, it is very evident this is dense, this is rare, because the light went away from the normal. So it depends on the pair of media, and there is a constant which is called as the refractive index or index of refraction, which defines how much it bends or how much it goes away. So for example, if I have, let's say air only, it doesn't bend at all. Look at it, the refractive index is 1. I increase the refractive index slowly. See how the light is bending now. Towards the normal. Can you see that, my dear warriors? Slowly the light is bending towards the normal. I hope you are able to see it. As I am increasing the refractive index, slowly it is bending towards the normal, Refractive index increases, So more the refractive index, more it will bend towards the normal. I hope this is absolutely clear. Okay, so that is what I have basically explained on this particular slide. Now let's come to the formulas, of course, and the diagrams. Okay, let's have a look. Say for example, we have this as the medium interface, and we have this as the normal. So this is the normal, this is the interface, this side is, let's say, medium number 1, this side is some another medium number 2. So what happens is light comes from here, let's say like this, and it bends, let's say like this. Let's say I show some arrow marks like this, like this. This is called incident ray. This ray is then called refracted ray. The angles are always measured with the normal. This angle is called angle of incidence. This is called angle of incidence. This angle R is called angle of, because this is refracted, so angle of refraction. So this is R, this is I, angle of incidence, angle of refraction. I hope this is clear. Chota Bhim, whatever doubt you have, please post, don't spam. If you spam, you will be put under timeout. So make sure whatever it is, you should clearly ask it in the chat box. Okay. Now, having said this, all these angles were also there over here. This was the normal. Here 34 degrees is incident angle, 20 degrees is basically your refracted angle. If I change it, you can see this is the new incident angle, this is the new refracted angle, correct? I hope you can see that, right? This is the incident ray, this is the refracted, the ray which bent after passing into another medium, correct? Now, like I said before, the wavelength and the speed will change, frequency won't change. All these things I have mentioned you, and the constant which decides how much it bends is called as the refractive index. Since the light traveled from medium 1 to medium number 2, the manner in which I define the constant is as follows: 1 mu 2. In your books, instead of the symbol mu, they might be using the symbol n, and instead of writing like this, they might also be writing it like this. All these things are the same thing, don't get confused. Okay? All these things are basically the same thing. Instead of mu, they use n. Don't get confused. 1 mu 2 means the light has traveled from 1 to 2, medium number 1 to 2. But while saying it, I will say refractive index of 2 with respect to 1. Refractive index of 2 with respect to 1. That is how it is basically called. This relative refractive index of medium 2 with respect to 1 is nothing but speed of light. This is the first medium in medium 1 upon the second medium, speed of light in medium 2. If you remember carefully, speed of light is nothing but frequency into the wavelength. Speed of light is frequency into the wavelength. Can you now clearly see the frequency definitely gets cancelled off? The frequency definitely gets cancelled off. So it is lambda 1 by lambda 2, where lambdas are nothing but their wavelengths. This is nothing but the wavelength of that particular light. So if the light in this case has bent towards the normal, this is dense medium, speed of light has reduced. That means if speed of light has reduced in the second medium, it became slower, C2 became small, so lambda 2 will also become small. So if wavelength was like this over here the wavelength will be a smaller wavelength. It will not be that large, it will be slightly smaller. Yes. So now some of you are also asking, Sir, won't it get reflected? Of course it will get reflected. When you see water, you see your reflection. When you see through glass, you see slightly your reflection and you also see on the other side. So whenever light enters another medium, obviously it also gets reflected. If 100 joules of energy is spent in light in incidenting it, then maybe 70 joules will go here, maybe 30 joules will go here. So 100 laddus, 70 laddus, 30 laddus, something like that. So not everything goes into the other medium, some of it might reflect back also. As you can see over here, law of reflection is always holding true. 40.5, 40.5. It is always getting reflected, but at the same time, refraction is happening. We are overlooking this part. We are just bothering about how the refraction works. We are not looking or concentrating on the reflection part. All right. I hope this is absolutely clear. Every week start, I will give the lecture planner. Yes. All right. No issues. Cool. Till this point, I hope this is clear. Now, it was also found that this particular ratio C1 by C2, which is lambda 1 by lambda 2, happens to be sine of whatever angle of incidence is there and sine of whatever angle of refraction is there. And this is basically called as your Snell's law. What is this called? This is called as your Snell's law. The ratio of the sine of the angle of incidence and refraction. So if you take some other angle, other refraction, other angle, other refraction, always that ratio of the sine of the angles comes out to be this particular ratio, which is a constant for a given medium. Hence, that is given a name upon the person who made it. That is why it is called Snell's law. Now, this term over here is always a relative refractive index when I write two things. But say for example, I just write mu2 or I just write mu1. Then whom am I referring to? The question mark over here is basically vacuum. So the light has entered from vacuum to that medium, maybe water, maybe glass, maybe diamond, maybe some jelly, maybe some transparent material. So this is what is usually given to you, which is called as the absolute refractive index. So coming to the point over here, this one is relative. This one is basically relative refractive index. But when you want absolute refractive index, then you just write it as something of that particular thing. This is always with respect to vacuum. And when you write 1 mu2 in terms of the absolute refractive indices, you can also write it as second term first. The second medium will come first in the numerator, then the first medium comes in the denominator. That is how the ratio comes out to be. Does frequency depend? Chota Bhim, first of all, don't spam. Write it once. Yes. So sin I by sin R is the refractive index. Correct. Frequency depends on the source. The light bulb which was emitting that color decides the frequency. Okay. Just to give you some examples of some refractive indices. Say refractive index of water. Refractive index of water is approximately 1.33, which is often taken as 4 by 3. Refractive index of glass is basically 1.5. Refractive index of diamond, it is very, very high. That is why it glitters and shines so much. It is like 2.4 or something like that. If you ask me refractive index of air, well, it is roughly 1 only. Even though it is slightly more than 1, it is like 1.000 some 3 or something. But you can take it as vacuum. There is hardly any medium or hardly any molecules, because those molecules are spaced out very, very far away in the case of a gas like air around us. So refractive index of air is roughly 1, just like for vacuum. Okay, so these are some values which you should know. Now I'll make some use of this, hold on, and I'll give you some more formulas also over here. You will also see that 1 mu 3, which is mu 3 by mu 1, can be written down as mu 3 separate here, mu 1 separate here. Deliberately, I will bring mu 2 here as well as here. Anyways, they cancel, equality is maintained. But the funny part is, what is mu 3 by mu 2? Light went from 2 to 3. So it is 2 mu 3. What is mu 2 by mu 1? That means light has gone from 1 to 2. Yes, so 1 mu 3 is 2 mu 3 into 1 mu 2. You can also write it as 1 mu 3. Bring this first. So 1 mu 2 multiplied by 2 mu 3. 2 mu 3 over here. How to remember this? Very easy. See, what was the starting alphabet? It was 1. So it starts with 1. See, what was the ending alphabet? It was 3. This is also 3. What is that middle number over here? Can you see that? That was the number 2. So automatically you can write it like this. Whatever is the first one comes first, last one comes last. In the middle, whatever is there is always going to be the same. Is always going to be the same. Also notice one more thing. If I write 1 mu 2, which is nothing but mu 2 by mu 1, and if I write 2 mu 1, it is nothing but mu 1 by mu 2. So they are both reciprocals of each other. They are both reciprocal. Reciprocal, you understand? X and 1 by x, reciprocal. You invert it. Numerator becomes denominator. Denominator becomes numerator. So therefore, can I say 1 mu 2 is nothing but 1 by 2 mu 1. So this is also an important formula. So let us just block whatever important formulas are there. This is one of them. This is another one of them. Obviously, this whole thing was very, very important. Snell's law in its extended form. And these are some common refractive indices of certain materials. Thank you, Kishore Mani. Should we remember all the values? I think it will be better if you remember it sometimes, but you need not have to remember usually. Usually standard things they give is glass and water. Diamond and all not needed. Air though is very obvious, like 1 only. So there is not much to remember. Okay, but it is better if you remember it. That's all. Let me show this to you by taking some examples, guys. Let me show this to you by taking some examples. Say the question is refractive index of glass with respect to water. That is what has been asked. How do you solve this particular question? Refractive index of glass with respect to water. Now, refractive index of glass with respect to water, technically, I don't know this answer directly, but indirectly maybe I can. This is the first alphabet, this is the second alphabet. So how about using this formula? This formula over here. Where did it go? This one, 1 mu 3 is 1 mu 2, 2 mu 3. Use this. How? Observe. First alphabet becomes first alphabet. The last alphabet becomes the last alphabet. And whatever is in between should be the same. Maybe I will take it as the air, or maybe as the vacuum. Maybe I will take it as the vacuum. Right? I can do that. That is one option. Or I have another idea. I gave you one formula here. 1 mu 2, 2 comes in the numerator, 1 goes in the denominator. That is, I think, even better. So why not write this as, this is the second one, so goes in the numerator. This was the first one, goes in the denominator. Mu g by mu w. Oh, I think now I know this. Refractive index of glass is 1.5. Refractive index of glass is 1.5. And refractive index of water is 4 by 3. 1.5 is 3 by 2. This 4 by 3 as it is. You can also write it as 3 by 2. This 4 is as it is over here. and this 3 goes on the top. 3 3s are 9 and 2 4s are 8. So this is the refractive index of glass with respect to water. Of glass with respect to water. Is this absolutely clear? How did we do this? 1 mu2 is mu2 by mu1. Mu2 I know, mu1 I know. Substituting it, I get the answer. Yes. Yep. I hope this is clear. I will read it. Should we, okay, I have answered all the other questions. All right, perfect. If there was another question, what is the refractive index of water with respect to glass, then the answer to that question obviously will be reciprocal of this. Reciprocal of this, hence it will be 8 by 9. Hence it will be 8 by 9. What about demand? Yes. Okay. Next important question, my dear students. Say for example, the question says, okay, the angle of incidence, say is nothing but 45 degrees and the refractive index is 1.41. Can you find the angle of refraction? Can you find the angle of refraction? That is the question. All right. Let's try to solve this question. Since it is clearly given incident angle, refractive index and angle of refraction has to be found. That means I will most likely use Snell's law. So, according to Snell's law, sine of angle of incidence upon sine of angle of refraction should be the refractive index. So, sine of 45 degrees upon sine of nothing but r is 1.41. What is sine 45? That is nothing but 1 by root 2. So, okay, sine r goes below. Actually, 1.41, I know the value, guys. It is nothing but root 2. It is nothing but root 2. Bring that root 2 here. Take that sine r on the top. So, 1 by root 2 and here again root 2 is equal to sine of r. So, therefore, what is sine of r? Root 2 into root 2 is 2. So, sine r is half. Whose sine is half? 30 degree. Awesome. So, the answer to this question is basically 30 degrees. Yes. I hope this is absolutely clear. Okay. So, Tabim, I am not answering that question because you are typing it 100 times. Sorry. Okay. So, r is equal to 30 degrees because angle of refraction is just coming out, sine of the angle of refraction is coming out to be half. Whose sine is half? Obviously 30 degrees. Now, in some questions, they might also ask you, can you find the deviation? Now, you might be wondering, sir, how do you find the deviation angle? How do you find the deviation angle? Let me tell you this. This is very straightforward, my dear warriors. So, the logic behind it goes like this. Imagine this is the normal, and we have this particular light ray going like this and bending like this, or this is like this and bending like that. Now, deviation means the light was actually supposed to go here. But because of the medium change, it got bent. So, this is nothing but your deviation angle. How do you find this deviation angle? It is a straightforward approach. See this. This much angle over here is angle of refraction. This whole angle is angle of incidence. That means if this is angle of incidence, even this thing over here is also angle of incidence. So how much will delta be equal to? Think about it. How much will delta be equal to? This whole angle minus r. So it will be I minus r. Same logic used over here. Notice this whole thing is basically, because the light went like that, this whole thing is the angle of refraction. This was angle of incidence. So the opposite angle over here is this much. The opposite angle over here is basically this much. So how much is delta going to be? This whole angle, which is nothing but r, minus this remaining angle I. So r minus I, the remaining is delta. So deviation is either I minus r or r minus I. So therefore, the deviation angle, deviation in refraction at a plane surface, is given by modulus I minus r. Why modulus? Because I don't know who is going to be big. So accordingly, we can choose bigger minus smaller. Accordingly, we can choose bigger minus the smaller one. I hope this is clear. Which first chapter, my dear students? Yes. For the JEE syllabus, we have a separate channel called as the Vedantu JEE English channel, exclusively focusing on JEE. This channel, I'll be focusing more on the KCET, COMEDK and PU. Yes, that is how it is going to be. So now coming back to this particular problem where the deviation was asked, what will I do? Deviation formula is modulus I minus r. Is the angle of incidence known? Yes, 45 degrees. Is the angle of refraction? Yes, we found it out. So 45 minus 30 is basically 15 degrees. Modulus of 15 degrees is 15 only. Positive's modulus is positive only. Yep. I hope this is absolutely clear. Yeah, we'll be doing electrostatics sometime later, not now, because right now your midterm are over and this will be one of the first few chapters which you'll be learning from the second book of your NCERT. That's why I picked this chapter. We'll also go to the first chapter of NCERT also of 12th standard from book 1. Don't worry. Okay. So having said this, and now that you have understood these basic concepts, let's do one more question, my dear students. Let's do one more question coming up on your screen. Imagine the question says, the light speed in glass for the light speed in glass is question mark. Frequency of light is 10 to the power 6 hertz. Find the wavelength in both mediums. Okay, so this is the question. Let's try to understand this. The speed of light in glass is asked, frequency of light is given, and what is the wavelength is also asked. See, think about it. This is the interface. This is the normal. The light will come like this and it will go inside like that. This would be your glass. This would be your air. Air, the speed will be more. How much will be the speed? The speed in air, the speed of light in air, we already know that's a standard value, 3 into 10 to the power 8 meters per second. And here, as soon as you go, the speed will reduce. So here, if the wavelength was this much, I think the wavelength will become smaller over here. It won't be as big as before. So the wavelength definitely will become smaller because the speed has become less. So how do we do this question? Refractive index of glass with respect to air is refractive index of glass only because air is just like vacuum. Okay. So therefore, understand this. This is as good as mu g by 1, which is as good as mu g only. And this thing we already know is speed of light in air upon speed of light in glass. So therefore, that is equal to mu g. 1 mu 2 is nothing but speed of light in the first medium upon speed of light in the second medium. We wrote this formula right over here. 1 mu 2 is speed of light in the first medium by the second medium. That's exactly what I'm writing down over here. Okay, so let's start substituting the values. Therefore, speed of light in air 3 into 10 to the power 8. Speed of light in glass, I do not know. Refractive index of glass 1.5 or 3 by 2. This is nothing but 1.5. Where did I give it to you? Right over here. Usually the value will be given to you, but still I have just memorized it for your sake. Okay. So 3 gets cancelled. 3 gets cancelled. Therefore, 2 comes on the top, and the speed of light in glass will come out to be 2 into 10 to the power 8 meters per second. 3 gets cancelled. 2 into 10 to the power 8 will be the speed of light in glass. So that is done and dusted. Okay, that part is done and dusted. Now we have to find the wavelength in both the mediums. So one thing is very clear, speed of light in air will be frequency into wavelength of light in air. What is the speed of, because wave speed is frequency into wavelength, standard formula. Speed of light is 3 into 10 to the power 8. Frequency 10 to the power 6. Wavelength is what I do not know. So 10 to the power 6, 10 to the power 8 will cancel, and you will be left with 3 into 10 to the power 2 is a lambda A. Therefore, the wavelength of light in that air is 300 meters. So 300 meters is the answer. Cool. Next part. If you talk about the second medium, which is basically glass, speed of light in glass is frequency into wavelength in glass. Speed of light in glass, we just figured it out, 2 into 10 to the power 8. Frequency doesn't change, of course. So 10 to the power 6 and lambda g. So therefore, 2 into 10 to the power 6, 10 to the power 6 will cancel. What is remaining is 10 to the power 2 is lambda in glass. So the wavelength in glass is 200 meters. These two zeros with 200 meters. So find the wavelength in both the medium. That job also we have done. So my dear students, we have done most of the models of the questions. Is this absolutely clear? Yep, absolutely clear how to solve these questions on refractive indices, deviation, and in general finding wavelengths or the angles itself. Okay. Now having said this, not every time will the light get refracted, and I will tell you why also. See this and understand these two scenarios. Let's say in this case, this is the rare medium and this is a dense medium. Now in the next case, I will reverse the scenario. This is a dense medium and this is basically a rare medium. So now what happens is, imagine light is incident from here like this. That light will definitely get refracted because it is going to the denser medium. It will bend towards the normal, and some part of it will also get reflected. Of course, you know that reflection also occurs. So this is how the light will go. For a small angle of incidence, small reflection, small refraction. Let's say I increase the angle a little bit. So let's say the light is coming at this particular angle. Then what will happen? Okay, no issues. It will still refract like this, and it will also get reflected over here. So as you can see, the light is falling in, it is getting reflected, and it is also getting refracted. Let's say I use some other angle now, maybe an angle like this. Then also I can see the light will still get reflected and refracted. It will reflect over here and it will refract over here. So definitely refraction is occurring and reflection is also occurring. So on this sides, you have basically the incident rays. These are basically the reflected rays, and these are basically the refracted rays. no matter what my angle of incidences were, it was always coming out on the other side. It was getting refracted as well as it was getting reflected. Correct? Till this point, absolutely clear. Nothing like not understood. Okay. Now let's do the other way around, from dense to rare. Now here comes the big problem. See, let's choose a small angle first, just like before. So what will happen is, if the light comes in at a very small angle, a part of it obviously will get reflected like this, and part of it will get refracted, but it will go away from the normal. So mind it, it is going away from the normal, correct? So this is how it will go. Okay, let's choose now a slightly bigger angle. Let's choose now a slightly bigger angle, maybe an angle over here like this. Now what will happen to it? It will get reflected for sure like this, and it will get even more refracted, maybe even here. It will bend more away from the normal. Oh, so it is still getting refracted at least. Remember, whatever I write over here again is incident rays. These are reflected rays, and this one is the refracted ray. Now what happens is, if I increase the angle beyond a point where imagine this ray, this particular ray which is incident, definitely it is getting reflected, no doubt. Definitely it is getting reflected, no doubt. But the refracted ray is almost like parallel to the interface. I mean, this is the maximum possible angle of incidence which is possible, because beyond this, you can't further refract the rays. You can't refract the rays beyond this point, because anything more than this, just imagine, if I have any particular ray beyond this, that's it. It can't get refracted. It will only get reflected. So as you can see, this particular ray is only going onto the reflected side. So it is totally internally reflected. This phenomena is called total internal reflection. This is called total internal reflection. Is this clear? So beyond a point, you can't refract it further. And the maximum angle of incidence is then called as the critical angle. And then the refracted angle will be obviously 90 degrees. The refracted angle will obviously be 90 degrees. If you want a formula for that, that also I will give you. Don't worry. Oops. What just happened? Okay, anyways, not sure why it is behaving weirdly. Okay, I'll just give it here, no issues. See, if I apply Snell's law for that red colored ray, sine of that critical angle upon sine of that refracted angle, which is 90 degree, light is going from dense to rare. So the light is going from dense to the rare medium. What is sine of 90, guys? Sine of 90 is nothing but 1. Usually you give the refractive index of glass with vacuum, water with vacuum, not vacuum with respect to glass. So usually dense comes here, rare comes here, usually, if you see. So if I have to flip these variables, I just have to write it 1 by mu denser medium's refractive index with respect to rare medium. So therefore, sine of that critical angle is 1 by the refractive index of the dense medium with respect to the rare medium. This is again a very important formula. Okay, sine of that critical angle is 1 by r mu d. So just to give you an example of this, say I tell you, listen, the refractive index of some medium is 2, diamond is 2.4, so some medium is there which is having refractive index of 2. Just imagine this. Cool. So what will be the sign of that critical angle? Well, it is 1 by refractive index of dense medium with respect to rare. Here the rare medium is vacuum. Rare medium is basically vacuum, and the dense medium is the medium itself. So this value is nothing but 2. So sine of that critical angle is 1 by 2. So therefore, what is that critical angle? The critical angle is 30 degree. Wow. So what do I mean by this sine of that critical angle is half, so critical angle is 30 degree. What do I exactly mean by that? What I mean is, observe this carefully. If this is the medium, this is basically your vacuum or basically air, then 30 degree is the maximum angle till which you can make the light fall on it, and it will go like this at 30 degrees. This is that critical angle of 30 degrees, where it will come out like this, almost parallel to the surface. Anything beyond this, that's it, it's just going to get reflected. Even angles like this, you will see it will just get reflected. So it is basically going to be totally internally reflected. But if you have angles like this, which are less than 30 degree, definitely it will come out. Okay, so if you have angles which are like this, definitely it will come out. It will get refracted. So I can clearly say that for angle more than 30 degree, it will get totally internally reflected, but more than equal to. And I will say that for your angles less than 30 degrees, it will get refracted. It will get refracted and reflected both, not just reflected. Refraction also occurs, reflection also occurs, but only for more than 30 degrees, you will see that it will only get reflected internally. Is this absolutely clear? We can also see it in the simulation. Imagine instead of air, I make this water, and this is air, this is dense, this is rare. As you can see, for small angles, definitely it comes out, it goes to the other side. As I increase the angle up to this point, maybe around some 80, 85 degrees, say 48 degrees of an angle of incidence, that's it. The ray after this only gets reflected. Before this, refraction, reflection, refraction, reflection, refraction gone, only reflection, totally internally reflected. Cool. Now, what are some of the interesting phenomena which are based on this refraction, reflection, total internal reflection and all of this? Let me tell you that. See, there are many such phenomena. I'll tell you one such phenomena over here. I'll discuss this. Imagine there is a swimming pool. Imagine there is a swimming pool like this. And you as a kid will get very fascinated looking at water and swimming pool and all of that. And let's say, oops, okay, some pandu is standing over here, and that pandu is seeing some fish which is swimming, or maybe it's dropped inside that lake or that swimming tank. Guess what? This pandu won't see the fish over there. This fish will be seen somewhere over here. This is basically the image of the fish. Obviously, the actual fish was here. So this is basically the object. The person feels the fish is over here. So one can even say that this one over here was the actual depth, whereas just this much over here was apparent. Apparent is something what is seen to me. This was the apparent depth. So the apparent depth inside that water is always less than the actual depth, and it only happens because of refraction phenomena. Because if you see the rays of light, how it will go means, it will go till here and it will get deviated away from the normal like this. It will go like that. So because the rays bending like this, because the rays are basically bending like that, it feels as if it is originating from somewhere over here. It feels, it is not actually originating, it feels that it is originating from over here. So when these rays which bend away from the normal enters anybody's eyes, they feel or perceive that the fish is over here, not over here, because of the bending of the rays phenomena. It's very interesting actually. And this apparent depth is actually the actual depth divided by the refractive index of this particular medium. Let's say it is mu. So the refractive index of this particular medium. Yes, a very interesting phenomena. And the reverse is also true, by the way. I don't know how many of you know this. Say for example, this was a pond, lake, ocean, whatever you want to call it. Okay. And let's say there is a peaceful fish. Chumma, it is swimming over here nicely. And there is some bird which is flying in the air, bird which is flying in that air like this. Okay. When this fish sees this particular bird, guess what? The bird appears somewhere over here. This is where the image of the bird is, and this is the actual object. So to think of it, this is nothing but the actual height, and this over here is basically the apparent height. And this apparent height is exactly opposite. I mean, here it was divided by mu, right? Here it was divided by mu, right? So here it is the actual multiplied by mu. Yes, instead of division, you now multiply because you have to make it more. Yes, you see it farther. Imagine a fish seeing a bird. The fish feels the bird is far away. That's what it feels like. It's really, really amazing. So how nature fools each other. You also might have seen that there are many more examples, like the bending of a spoon, in a glass of water, or even the twinkling of stars, in the sky, stars in the night sky, or even the early or late sunrise or basically set. All these are due to refraction. I'll tell you why. See, if you put spoon in glass of water, the rays, when they come out from water to air, they will bend. So you'll feel that the spoon has been bent. You will feel, you try it out on your own, you will see that. Yes. If you also see the twinkling of stars in the night sky, why it happens is because the light which is coming from very, very far away stars, okay, very, very far away stars, when they have to reach the earth, these rays, they have to pass through the atmosphere. These rays have to pass through the atmosphere. The Earth's atmosphere is over here. This is the Earth's atmosphere. Check this out. This is the Earth's atmosphere. So what happens is these light rays which come from that distant stars, because the air is constantly moving, hot wind is going up, cold wind is going there, some cyclone is there, wind is moving, breeze is there, somebody walks, something will change. So these rays, they will keep going like this. Then once they will go like that, then once they will go here, then once they will go here. So it keeps fluctuating. They keep basically fluctuating. fluctuate due to variations, and that is why sometimes the light will enter and then it will not enter, not enter, then you will not see it, again see it, because the light is going here, there, because of the variations in the wind. And that is the reason why you see the stars to twinkle in the night sky. Correct. Even the early sunrise, sunset is because of that only, because see, the sun might be here. Example, this is the sun. By the way, this was the earth. Yes. So what will happen is the rays from the sun, when they enter the earth's atmosphere, they will get refracted due to the air, and they will come and meet the person standing on the earth like this. They will get bent towards the normal, because vacuum and air, small difference is there, a small deviation will occur. So the person will feel that the sun is over here. The actual sun is here, but the sun, he will feel that it is over here. So you are seeing the sun even after some time because of the refraction phenomena, or maybe during sunrise you are seeing it before. So this is again due to refraction. Is this absolutely clear? Amazing, right? Okay, there are even more phenomena, my dear students. Imagine you are in a desert. The air close to the sand is very basically hot. Very hot air. As you go on the top, the air becomes colder and colder. So it becomes cold over here. And what is the difference between hot air and cold air? Well, the air which is hot is basically rarer. That means the refractive index is less. And the air which is basically colder, okay, so that is basically slightly dense air. That means the refractive index is more. This is one phenomena which can occur. And then there is another exact opposite which can occur, where the bottom part is basically cold air, just like over here. The bottom part was hot. The bottom part, imagine, is basically cold air. That means this is basically dense. That means refractive index is more. And the top part is basically, let's say, hot. That means this is rare. That means the refractive index is less. Any of these two things can happen. Now, what happens in either of these cases? All right, very good, Shivani. What happens in either of these two cases? See, observe carefully. Just imagine our sky, right, is blue in color, correct? The sky is blue in color. So the rays from the sky, as they enter our Earth's atmosphere, they are going from rare medium to dense medium. So think of some layers. Now. This is cold. This is slightly less cold. This is slightly warm. This is even more warm. This is even more warm, like that. Think of it like layers. How will the ray behave now? Think about it. This ray will go like this because it is going from rare to dense. What will happen? It will bend towards the normal. It will bend basically towards the normal. Similarly, over here, if the bottom part is hot, and this is that sky over here emitting blue color, as you go from dense to rare, the light will bend away from the normal. So this particular light ray will definitely bend away from the normal. Now the problem happens here, not over here. Because here no problem, because the light will just keep bending towards the normal, as it goes from dense to more dense layer. The problem happens here because it is going from a dense layer to a rare, to a more rare, to even more rare. Just imagine as it bends even further, at every single interface, what is happening is the angle of incidence is increasing. Imagine there comes a point where it becomes so much that the angle of incidence crosses the critical angle. If it crosses the critical angle, it can no longer refract, but it will only reflect. And it will reflect and go like this. And imagine there is some person standing over here. Imagine there is some person standing over here. What will that person feel? That person will feel, oh my God, there is this ray which is coming from here. Maybe he feels like there is water. There is water over here because it is bluish in color. This is called as a mirage. This is called as a mirage. Got it, everyone? Yes, this is called as a mirage. Now you might be like, sir, this is so cool. This is how the mirages are formed. If you see on a hot sunny day, you feel like there is some watery thing somewhere very far away. This is the working principle of that. What about the rivers? In the rivers, there is no problem here, but imagine there was some person, some vehicle, some ship, some thing over here. Just imagine some person or some ship or something is there over here. Okay, and the rays which are now going to come from the ship will go like this. Some tank, some vehicle, they are going now from a dense to rare, so they will bend away from the normal. So what will they do? They will basically bend away from the normal. Away from the normal, correct, like this. Away from the normal, then again away from the normal. Every single instance, see what is happening. The angle of incidence is increasing, and then maybe the angle of incidence increases so much that it crosses the critical angle. It no longer can refract, so it will then just get reflected. It will just get reflected, correct. It will just get reflected like this. And now just imagine this enters some Pandu's eye over here. Imagine some Pandu is seeing this ray coming. He will feel, oh my God, this particular ship is somewhere over here. He feels like it floats. It floats. Actually, this tank, this vehicle, this person, the ship is here, but he feels like it is over here. This effect is called as looming. What is it called? It is called as looming. Interesting? Understood? Very cool. In fact, you also will see that the functioning of optical fiber cable is also based on the phenomena of total internal reflection. This is basically a dense medium. And there is air, of course, outside. Once the light is inside this particular fiber, the medium's density is chosen in such a way, the refractive index is chosen in such a way, no matter what the angle is, it will never ever escape. So it will always get reflected internally. So total internal reflection in an optical fiber. Optical fiber is basically a technique of sending signals through transparent medium without using electrical signals. So the electricity does not go, light travels, and light is a better traveler than electricity because electricity will fade away. Some noise will be there, it will get disturbed. Electricity will consume a lot of energy, and also as it moves more and more, it will lose its energy and it will die out. But light, well, light coming from stars, it's millions of years away. So light can travel farther, it is better, no noise will affect it. Even if there is some surrounding disturbance, nothing will affect it. So that is why you use optical signals rather than electrical signals. So your internet which comes in your home and maybe even some of the audio devices, they use optical fiber network because the transmission clarity is very, very good. So that is based on that. Yeah. The rainbow formation is based on a completely different thing. It is based on a phenomena called as a dispersion. Yes, refraction is also there, but dispersion is also going to play a very important role. If you ask me about basically diamond, some people ask me, sir, how does this diamond function, sir? Basically, why does that high refractive index have so much of a role in that? Okay, so imagine this is some, I've just taken some random thing over here. Okay, imagine this is basically diamond, and a diamond has very, very high refractive index. So by chance, if light enters also, okay, even if light enters, let's say it enters here, most likely what will happen is the light will, once it is inside, right, that's it, it will be at an angle much more than the critical angle. So the light can't go out, so it will get reflected. And these sides are chosen in such a way that wherever it falls, it gets internally reflected again. Again, it gets internally reflected. Again, it gets internally reflected. Again, it can't go out because you can see the angle of incidence is very huge. So it will again get internally reflected maybe. Okay, maybe it gets out from here. Maybe some other light coming from here, might again get reflected many, many times. Many, many times. Some other light which is falling from here might again get reflected many, many times like this maybe. Okay, so I'm just showing some random things over here. Oops. Just imagine it is coming like this and it is coming out like that. Okay, so because of multiple reflections, multiple total internal reflections, it basically shines and you get that glitter. So that's why when you use a higher carat diamond, means there are more cuts. There are more cuts in it. Because of those accurate cuts, it reflects many times and it glitters before the light comes out. That is why a diamond sparkles. Got it, my dear warriors? Many of you did not know about this, I bet. Yeah. So these are some interesting things about refraction, apparent depth, total internal reflection, speed of light, wavelength, and so on and so forth. Correct. So that is what we have learned. All right, let's see some questions on that. We will see lenses and everything in the next class. Yes, we'll be seeing lenses and everything in the next class. I think today we have just done refraction at a plane surface. So lenses, I will omit it in the title later on. Okay, lenses will do it in the next class. But I hope till now everything was absolutely clear. We will be doing more questions in the next lecture. Correct. Main thing, have you understood? Have you enjoyed? Don't worry about, sir, which chapter are you doing next? Which chapter am I doing then? All that is secondary. Shreyas Sir will keep teaching. Your job is to keep learning. Shreyas Sir will keep teaching. Your job is to keep learning. You keep learning, and within no time, you would have learned so much. Because if you see me on JEE and NEET channels also, same thing I've done. See, students are like, sir, will you complete this? Will you complete? I'm like, everything will happen. Don't think about it. I have thought about it in my head. And now almost everything is done on the JEE NEET channel. Now it's going to be revision phase. Same thing I want with you guys. If you stick with me till the end, right, everything will be done on YouTube over here. And you will feel confident about solving problems. You will love physics. See, when you love something, that's when you will actually do it. When you feel it, when you see it. Today you saw what refraction is and how total internal reflection occurs and, all those medium changes, how it matters. So that is what I want you to get, the feel of the situation. Okay, so love it, enjoy it, learn more and study more and solve more, and obviously this will lead to more marks. So don't be disappointed if your midterm marks or previous preparation was not up to the mark. Captain Shreyas Sir is with you. Okay, thank you for liking, thank you for subscribing. God bless you. God bless you all. Thank you so much. Take care. Have a great time. Bye bye.